Hello everyone, welcome to online lecture series on Fourier transforms. This is lecture number 10. In this lecture, we will solve some problems on Fourier transforms and apply Parseval's identities. In the last lecture, we derived Parseval identities for Fourier transforms and Fourier sine and cosine transforms. For reference purpose, again, I am giving here the identities. These are Parseval's identities for Fourier transforms. Keep in mind these two identities. And these are Parseval's identities for Fourier sine and cosine transforms. We have four identities here. Now let us solve some problems on Fourier transforms. First problem is find the Fourier transform of f of x defined by f of x is equal to 1 if mod x less than a and 0 if mod x greater than a. And hence prove that integral 0 to infinity sine square ax by x square dx is equal to pi a by 2. In this problem we have two parts. First one is to find Fourier transform of f of x and second one is to derive the value of the given integral. So for solving the first part, we consider the Fourier transform of f of x, and we all know that Fourier transform of f of x is f of x is given by integral minus infinity to infinity f of x into e power isx dx. Now let us split this integral from minus infinity to infinity as minus infinity to minus a to a plus a to infinity, because in the definition of the function f of x, it is given as 1 if mod x less than a and 0 if mod x greater than a. Mod x less than a means x is in the interval minus a to a, that is minus a less than x less than a. And if mod x is greater than a, then it means that x lies in the interval minus infinity to minus a union minus a to infinity, that is a less than x less than infinity. So accordingly we split the integral in the definition of Fourier transform. Now in the interval minus infinity to minus a, f of x is 0. Therefore here in place of f of x in this integral we write 0. And in the interval minus a to a, f of x is 1. So in place of f of x here we write 1. And again in the interval a to infinity, f of x is 0. Therefore this f of x is 0 here. So after substituting the values of f of x, we will remain with the integral minus a to a 1 into e power isx dx, that is equal to e power isx by is, because integral of e power isx is e power isx by is within the limits a to minus a to a. Now let us substitute the upper limit, which is e power isa, minus lower limit, that is e power minus isa. So we obtain e power isa minus e power minus isa by isa. But we know that e power minus I theta is equal to cos theta minus I sin theta, and e power I theta is equal to cos theta plus I sin theta. Therefore e power I theta minus e power minus I theta becomes 2I sin theta. So we obtain 2I into sin as by is. I in the numerator and denominator gets cancelled and we remain with 2 sin as by s. Therefore the Fourier transform of f of s, that is f of x, is given by 2 sin as by s. So we completed first part in this problem. Now to derive the value of the integral which is asked in the question, we use Parseval's identity on Fourier transform. Second Parseval's identity on Fourier transform, which states that integral minus infinity to infinity mod f of x whole square dx is equal to 1 by 2 pi times integral minus infinity to infinity mod f of s whole square ds. Now let us substitute the values in the left hand side integral as well as right hand side integral. First consider the left hand side integral. Integral minus infinity to infinity mod f of x square can be split as integral minus infinity to minus a mod f of x whole square dx plus mod a minus a integral minus a to a mod f of x whole square dx plus integral a to infinity mod f of x whole square dx. And right hand side is 1 by 2 pi integral minus infinity to infinity mod f of s square. In place of f of s, we can substitute 2 sin as by s. And again coming to left hand side, here the value of f of x in this case is 0. The value of f of x in this case is 1. And the value of f of x in this case is 0. Therefore, after substitution, we have integral minus a to a 1 dx is equal to 1 by 2 pi integral minus infinity to infinity 2 into sin as by s whole square ds. Integral of 1 is x within the limits minus a to a, which is equal to 4 by 2 pi integral minus infinity to infinity sin square as by s square. That is equal to, that implies a minus of minus a. When we substitute the limits here, we get a minus of minus a, that is 2a, is equal to 2 by pi times integral minus infinity to infinity sin square as by s square ds. Now, integral minus infinity to infinity sin square as can be written as 2 times integral 0 to infinity sin square as by s square, because sin square as by s square is an even function, and hence it can be written as 2 times integral 0 to infinity. Therefore, we obtained integral 0 to infinity sin square as by s square ds is equal to pi a by 2. Hence, the value of the integral 0 to infinity sin square ax by x square dx is equal to pi a by 2. So, Parseval's identity is applied to derive the value of this integral. Let us see another problem. Find the Fourier transform of f of x defined by f of x is equal to 1 minus mod x if mod x less than 1 and 0 if mod x greater than 1. And by using Parseval's identity, prove that integral 0 to infinity sin x by x whole power 4 dx is equal to pi by 3. Again, this problem also has two parts. First one is finding Fourier transform of the given function f of x and applying Parseval's identity to evaluate the integral. So, first let us find the Fourier transform of the function f of x, which is given by integral minus infinity to infinity f of x into e power isx dx. Again, we split the integral minus infinity to infinity as minus infinity to minus 1, minus 1 to 1 and 1 to infinity. Substituting the values of f of x in each interval, in the first integral the value of f of x is 0, and in the second interval the value of f of x is 1 minus mod x, and in the third integral the value of f of x is 0. So, after substituting, we have integral minus 1 to 1 minus mod x into e power isx dx. Now, because we have modulus of x here and we know that mod x is equals to minus x if x is less than 0 and x if x is greater than or equal to 0. Therefore, according to the definition of mod x, we again split the integral minus 1 to 1 as minus 1 to 0 plus 0 to 1. In the interval minus 1 to 0, because x is less than 0 in that case, modulus of x is equal to minus x, and hence this become 1 plus x. And in the interval 0 to 1, mod x is equal to x, therefore this becomes 1 minus x here. Now, applying by parts, integration by parts in these two integrals, we get 1 plus x into e power isx by s minus e power isx by I square s square within the limits minus 1 to 0, and here 1 minus x into e power isx by s plus e power isx by I square s square within the limit 0 to 1. Now, let us substitute the limits. In the first term, upper limit is 0, so we get 1 by is minus 1 by I square s square minus lower limit is x is minus 1, so this term becomes 0 and this term becomes e power minus is by I square s square. Similarly, if we substitute the limits in the second integral, we get this term. So here 1 by is and minus 1 by is cancels and we have e power is plus e power minus is minus 1 minus 1. So it is minus 2. Therefore it is e power is plus e power minus is minus 2 by I square s square, that is equal to 2 cos s, because e power I theta plus e power minus I theta is 2 cos theta. So this is 2 cos s minus 2 by I square s square. We take out 2 outside, we get 2 by s square into 1 minus cos s, because I square is equals to minus 1 here. Therefore, we derived the Fourier transform of f of x as 2 by s square into 1 minus cos s. Now to derive the value of the integral, we apply Parseval's identity on Fourier transform. Again here we consider the second Parseval's identity on Fourier transform, which states that integral minus infinity to infinity mod f of x square dx is equal to 1 by 2 pi times integral minus infinity to infinity mod f of s whole square ds. Now the integral in the LHS is split as integral minus infinity to minus 1 plus integral minus 1 to 1 plus integral 1 to infinity. And in the interval minus infinity to minus 1, f of x is 0. And here in the interval minus 1 to 1, f of x is 1 minus mod x square. And again in the interval 1 to infinity, f of x is 0. And in the right hand side, we substitute mod f of s as 2 by s square into 1 minus cos s whole square ds, which implies that integral minus 1 to 0 1 minus mod x whole square dx plus integral 0 to 1 1 minus mod x whole square dx is equal to 4 by 2 pi integral minus infinity to infinity 1 by s square into 1 minus cos s whole square ds. And in the interval minus 1 to 0 mod x is minus x, therefore this becomes 1 plus x. And in the interval 0 to 1 mod x is plus x, so this becomes 1 minus x whole square. So upon integrating this, integral of 1 plus x whole square is 1 plus x whole cube by 3, and integral of 1 minus x whole square is 1 minus x whole cube by 3 into minus 1. And the left hand side, the right hand side is here in place of 1 minus cos s, we write 2 sin square theta, because 1 minus cos theta is equals to 2 sin square theta by 2 is 2 sin square theta by 2. So in place of 1 minus cos s here, we have written 2 sin square s by 2. Now coming to left hand side, after substitution of limits in these two terms, we get 2 by 3, which is equals to 8 by pi into integral minus infinity to infinity sin power 4 s by 2 by s power 4 ds. So after simplification, we get integral minus infinity to infinity sin power 4 s by 2 by s power 4 ds is equal to pi by 2. Now this sin power 4 s by 2 by s power 4 is an even function, and hence integral minus infinity to infinity can be written as 2 times integral 0 to infinity. Therefore 2 times integral 0 to infinity sin power 4 s by 2 by s power 4 ds is equals to pi by 2, because this function is an even function. Sin power s by 2 by sin power 4 s by 2 by s power 4 is an even function, and hence the value of integral 0 to infinity sin power 4 s by 2 by s power 4 is equal to pi by 24. But in the problem, we are asked to derive integral 0 to infinity sin power 4 x by x power 4. So in place of s by 2, we are substituting x. Upon differentiating this, s by 2 is equal to x, we get ds is equal to 2 times dx. Now if we substitute these values in the above integral, we get integral 0 to infinity sin power 4 into, in place of s by 2, we write x divided by s power 4 is 2x power 4, and ds is equal to 2 times dx, which is equal to pi by 24. So integral 0 to infinity sine power 4x by x power 4 dx is equal to 8 pi by 24, because we have 2 power 4 here, 2 power 4 here, 2 becomes 1 by 2 cube, that becomes 8 here. So this is 8 pi by 24, that is equal to pi by 3. And hence integral 0 to infinity sin x by x whole power 4 dx is equal to pi by 3. So here also we applied Parseval's identity to derive the value of this integral. So we have another problem here. Find a Fourier transform of f of x, where f of x is defined as 1 if mod x less than 1 and 0 if mod x greater than 1. And using Parseval's identity, prove that integral 0 to infinity sin t by t whole square dt is equal to pi by 2. The problem number 3 can be solved similar as in problem number 1, and hence it is left as an exercise to you. So hope you understood these problems. So in the next lecture, we'll continue with the Parseval's identities on Fourier sine transform and cosine transform. Thank you for watching the video. Thank you.